Hey, this is Alex Horton. Out sick today, but hopefully still doing a good lesson on Introduction to Energy. First up, if someone told you energy is also conserved property, what could you tell them back? Well, let's think about that for a second. We had momentum as a conserved property, and what that meant was that momentum can be moved around, but it can't be created or destroyed. And so in this case, if energy is also a conserved property, it means you can move it around, you can transform it into different types, which is one way we think about it. But the energy can't just come from nowhere, or it can't just disappear either. And this is going to form the basis for a problem-solving strategy, a lot like the way we solved the big multi-object momentum problems last time around. All right, so getting started. We're covering energy concepts, introduction today. Date's wrong, oh well. What you're going to do is know about what energy is, how it's measured, how to categorize it, mechanisms to store energy, and then we're going to start problem solving with it pretty much right away. So there's a couple different ways to think about it. First up, let's say I threw a brick, and you guys are probably glad I'm out sick and not actually throwing the brick here, but okay. The brick is a big macroscopic object. Macroscopic means large scale. And when you throw it, pretty much all of the brick is headed the same direction at the same speed. And that is called kinetic energy. So the fact that the brick is in motion means that there's energy stored in the brick. Now what's weird is that there's actually motion in the brick all the time, even if you don't throw it. So if you just have a brick and it has a certain temperature that's not absolute zero, as in it's not super cold, it turns out that the atoms and molecules within the brick are wiggling and bouncing back and forth. They're held in place by their chemical bonds, but that really small scale, disorganized, chaotic motion is called thermal energy. And so you guys associate this with a temperature, although I want to be clear that temperature, heat, and thermal energy are three different things. So thermal energy is the fact that there's motion in the brick, even if you don't throw it. A couple other options. What if I lifted the brick up above the desk? First of all, if it was resting on the desk, then it's called the ground state. The brick is as low as it can go. And in the ground state, it doesn't have any potential energy. But as I lift it up above that level, then it's storing potential energy because it's located within Earth's gravitational field. So an object's location within any kind of field can also give it energy. Keep in mind that gravity is not the only type of field force out there. There's also electromagnetism, strong nuclear, and weak nuclear. So there's about 4 total forces that we know of, and the location of an object within that can definitely account for some of its energy. Last up, you can have the field itself be a mechanism for storing energy, and when we talk about it this way, what we're talking about is light. And when I say light, I don't necessarily mean the visible kind. I also like ultraviolet light, that's my favorite color, infrared, radio waves, microwaves, x-rays, gamma rays. There's a whole bunch of different kinds of light, not just the kind you can see, and all of those store energy too. And that's based on an electromagnetic field oscillation. So, just to summarize here, stuff is moving, stuff is located within a field, or the field itself are 3 different ways to store energy. And our names for these tend to be kinetic, thermal, potential, and radiation. A couple different kinds here. All right, well, so that's kind of like the ways to think about it. Let's keep going here. We'll come back to that soon too. So I mentioned earlier there are 4 different kinds of forces. Strong nuclear holds together the nucleus of the atom. The weak nuclear we'll talk about towards the end of the course. Hold that thought for a couple months. Electromagnetism is a long-range force that has to do with interactions between charges, like protons and neutrons. So when you guys use electrical energy, that's based on electric fields and electrons moving within wires. So electricity counts as energy stored within electromagnetic fields. We also mentioned that light, including all the kinds you can't see, are based on electromagnetic fields. And then last up, we talked about lifting the brick up so that it's above the ground. Ground state is when it's on the floor. Excited state is when it's been lifted up. And just the fact that the brick is up in the air now means that it's got energy built into it, and we call that gravitational potential energy. So let's keep going now. So we talked about lifting and dropping bricks. If I lift the brick up, what kind of energy have I given it? Potential. And if I let go of the brick, what kind of energy does it turn into? Kinetic. And then right after it hits the table, instead of large-scale organized motion, that'll be vibrating at a really small disorganized level, and a lot of the energy in the brick will actually convert to thermal, as well as have sound waves blast out through the room, and that sound can also carry energy with it. Now you might be thinking, electrons near nuclei, same thing, different thing. Well, the Earth's gravitational field is pulling the brick down, and the nucleus of the atom is pulling the electrons down. So electrons near a nucleus actually experiences the same kind of potential energy, and when they get lifted up, they're storing energy in potential form. When they fall back down, they have to release that energy somehow, and that comes out as light. We'll go into a bunch of these other ones when I'm back in school here. We'll come back to this topic here. All right. We will also do a bunch of these demos later, but I think we can do Energy Skate Park right now. Let's load that up. So we're going to go to playground mode, put a little bit of track down, and what we're going to do with this is look at how energy is conserved. Just going to make a simple system right now. We definitely want to turn on the bar graph in the grid, and we'll have no friction at first. Not super realistic, but okay. All right. So when I put the skater up top here, what kind of energy is she? What kind of energy is she storing? And because she's high up above the ground state, she's got gravitational potential energy. It's based on her position in a field. If I let go of her, by the time she rolls down to the bottom, she'll be moving really fast. At that point, what kind of energy is she going to have? Kinetic. And then, because I turn friction off, we're not converting any to thermal. When I let go, do we expect the total energy in the system to change? No, energy is a conserved property. So we're looking at that bar graph there. That yellow line will always stay the same, but you can shift which kind of energy she's got depending on where in the system she is. And now if I turn on a little bit of friction, what do we expect to happen? We expect some of the large-scale organized motion to turn into small-scale disorganized motion instead. And that'll convert it to thermal energy instead of kinetic energy. That'll happen gradually here. Is the total energy changing? No. Here's an issue though. Sometimes it's hard to keep track of thermal energy. So you might feel like the energy is leaving, and you might call it an open system. Something where the energy is leaking out, because tracking that thermal energy can be very difficult in real life. But it's important to understand that the total energy always stays the same. It's never really changing. All right, let's hop back to that. Yeah, we could do this. Let's do that too. Okay, so we've got two different atoms. If they have electron clouds around the outside, the electrons are like charges and they will tend to repel if they get too close. On the other hand, they form what's called a dipole, which is positive and negative charges lining up to attract some of the time too. So basically, you can't get them too close or they repel, but they don't want to go super far from each other either. And so you can move these back and forth, and if these were two atoms wiggling, what kind of energy would you call this now? Because this is small-scale disorganized motion, I'd call this thermal energy. And this might be happening within the brick or within whatever bigger object you're looking at. One thing you can do is, if you can see this red line, it asymptotes out to 0 here. If you have more energy than that, then you can basically escape the system. So that's something to think about too for orbits and rocket ships and stuff like that. Alrighty, we'll keep going here. Yeah, we're going to skip that and come back to that tomorrow, hopefully when I'm back, maybe by Wednesday, we'll see. Okay, entropy. Entropy is the saddest idea in the entire universe. It is the idea that stuff tends to get less and less organized over time, overall. You might be able to organize one place, but in the process you've made some other place much, much, much worse. So like, let's look here in the first picture. If these are little atoms and they were all organized, and we let them just do their thing, are they ever going to get back to that level of organization? No, they're going to tend to spread out and act chaotically. Same thing with this nice ice crystal here. Which side is more organized? This side or this side? It's definitely that side's more organized. This is less organized, so that has a higher level of entropy. Here's a bunch of gas in a jar. If we open this valve, what's going to happen? It's going to spread out. Can we ever get the gas back without using a whole bunch of energy from something else? Nope. So that's going to tend to go back. And last up, if we have soccer balls rolling uphill or downhill, which way do they go? They go downhill, and they convert all of their kinetic energy to thermal energy eventually. So that's something to think about too, that stuff tends to get more and more disorganized over time. And in the process of this, they tend to settle down, like literally down, depending on which way the gravitational field or whatever other kind of field is pushing. And they'll release their energy from a organized potential or kinetic form into a disorganized thermal form, typically. We'll talk about why this is a super sad idea later. But just for one quick example, let's say you worked out super hard and you had a couple muscle, like micro tears. And so you needed to fix about 10 grams of muscle. What you might do then is go eat a giant, like 200-gram hamburger. And in the process of your digestive tract completely taking apart that hamburger and disorganizing it, you'd then have the ability to organize the 20 grams of muscle in your own body. Is it a good deal overall for the universe? No. Overall, we disorganized a bunch of hamburger, right? And just to be able to fix a couple muscle micro tears. So overall, you can make one spot better, but in the process, you make somewhere else a lot worse. And that's why the tendency is always to increase entropy over time. This has to do with how energy is converted, by the way, in the long run. In the long run, the thermal energy will kind of dominate the system, and that thermal energy spreads out. Once it's spread out, it's really hard to get back in any way. We will come back and look at this again later, but hopefully you got enough of an intro to start thinking through this. We're going to jump now to actual equations for energy. First one is potential energy, which is where an object is high up in a field. We're specifically going to work with gravitational potential energy. And all you need to do is take the object's mass in kilograms times 9.8, you can round to 10 meters per second squared, g, times the height in meters. That's it. You multiply those three things, you've got the potential energy. The potential energy is measured in joules. Joules of energy. You can put a capital J there for that. Okay. There are other kinds of potential energy too, even though we're going to focus primarily on gravitational potential energy. You can have potential energy stored in springs, in twisted things like elastic bands. You can have energy, as we mentioned, in electrons orbiting atoms. And when the electrons fall down, they release a color of light proportional to how far they fell. So we're going to talk more about that. Hold that thought till like Unit 6 or whatever, a couple months. We'll come back to that too. But basically, there's other ways to store potential energy besides the gravitational form, which is the one we're going to focus on. Other things we're going to do is check out kinetic energy. M is for mass, V is for velocity. It's important to note that the V is squared, so kinetic energy is 1/2 mv squared. Again, energy is measured in joules. So it's the same as in potential energy, the unit labels are. And bigger, faster things definitely store more energy. Now, what's interesting is you could use that same equation to calculate thermal energy if you were willing to track it atom by atom by atom, or molecule by molecule. So that equation also works on a microscopic scale to track thermal energy, just nobody would ever want to do it that way because that's too many objects to track. So we just stick with that for the big organized motion called kinetic energy. Now, just like we started out today, the total energy is the same both before and after any kind of event. Energy might be converted to different forms, and we have to be able to keep track of where the energy went. So we're going to try to define closed systems, systems where nothing leaks in or out, and we're tracking all the objects where it's not missing from. And at that point, we should be able to problem solve this. One other thing we can do is we can transfer energy back and forth. So work is defined as the transfer of energy. It's a really flexible idea. You can define a lot of different energy concepts as work done. Let me give you some real quick examples. If I lift some barbells up, then I have done work on the barbells, and the barbells have had work done on them by me. So for me, I'd call that a negative amount of energy. I lost energy, and the barbells gained energy in that process. So you want to be kind of clear when you say it, which direction the energy is being transferred. So like your car, your engine transfers energy into the vehicle. And process, of course, that's coming out of your gas tank. But basically, yeah, which direction the work is done is important. Okay, things that don't count. if you push on something for 0 distance, you haven't done anything effective. So like pushing on a stationary wall, you are not adding energy to the wall. It doesn't work like that. Also, it's important that the force and distance match up in direction. So let me give you an example of this. Let's say you're coasting on a bicycle, and you're definitely pushing down on the bicycle with your weight, but you're coasting to the right. Those are perpendicular directions. The direction you're pushing and the direction you're moving are not lined up. That does not count as work. So the force and distance involved in this have to be matching directions. All right, next idea. You guys may or may not know it, but I'm actually like one of the more powerful people in the world. And here's how you know this. I was watching the world's most powerful man competition, and there's just some giant, brutishly strong guys, and they're doing things like lift up logs or take these giant boulders and roll them across a field. Or my very favorite one was this guy puts on a harness in a small compact car with the floor cut out, and the harness, of course, is connected to the car. And at one point, he stands up and he lifts the car. And I'm like, sweet, dude, I bet I could do that. So I go to my garage and I too just like lift my car. It was awesome. I did the same thing that the world's most powerful man did. Now, here's the subtle difference. It took him 1 second to lift the car, and I had a whole bunch of jacks set up, and I was able to lift my car in about 60 seconds, which is not a bad time, right? But like, definitely not as fast. So he's more powerful because the amount of time it took to get all that done is much shorter for him. So he did this, we both did the same thing. Like he lifted his car, I lifted my car. We did the same amount of work. We transferred the same amount of potential energy into the car by lifting it against a gravitational field. But the difference is he did it quicker, and so he's got more power. Power is how quickly the work gets done. It's measured in watts. That's a compound unit of joules per second. You've probably heard about this already for light bulbs. It's the rate of energy consumption of something. And one thing that nobody ever remembers, I can never remember this either, is that 1 horsepower is 746 watts. But I just rounded to 750, it's close enough. And that way you can be like in the gym, you know, one of those spin bikes or treadmills or something, and you can look at it and you'd be like, oh, I'm doing, I don't know, 350 watts, or 325 watts, I mean. And you're like, oh, sweet, that's half a horsepower. So yeah, being able to convert to and from horsepower is pretty handy. 1 horsepower is about 750 watts. Okay, I think we are going to do some simple problem solving today, and then I'll try to get you a tutorial on how to do lull diagrams and other stuff tomorrow. And yeah, let's, you guys can switch to your handout now, and I will try to go upload a second video on how to solve that handout. Hey, I'm back. This time I'm doing that example on the PowerPoint. So it looks like we've got Ryan Finn on a trampoline. Excellent. Okay, we've got 3 teenagers. They're all moving fast right when they're on the trampoline. So what kind of energy are they starting out with? Well, they're going to all be moving fast in organized ways. That's kinetic energy. So you could say kinetic energy 1 plus kinetic energy 2 plus kinetic energy 3. That's the kind of energy they have before they all start to bounce. Okay, what else is going on afterwards? So it looks like all of the energy is going to be transferred to just one kid. And we are supposed to be finding out how high the kid goes. So, okay, so if they're going up really high, then it's their position within a gravitational field. So we're looking at gravitational potential energy for the way that the energy is showing up afterwards. So what I'm doing right now, just in case it wasn't clear, is I'm setting up a law of conservation of energy style problem. I'm saying that the total energy before equals the total energy after, and that it's a conserved property. So if we can find out how much energy was in the system beforehand, it has to be the same amount afterwards, even if that energy has moved around or been transformed. All right, next up, I'm going to go get my equation out for kinetic energy. It's 1/2 mass times velocity squared. That's going to be for each of the 3 kids. And then, oops, okay. There we go. So we're going to do that 3 times, 1 for each kid. Yep. And then on the right side of it, we are going to have the equation for gravitational potential energy, which is mass times gravity times height. Alrighty, so that's an equation that's all set up now. At this point I can plug in some values. Let's see, 1/2 of 60, that's going to be 30. And then the velocities are 7 squared, which is 49. And there's 2 of those kids. And then the third kid is not going quite as fast because he's getting ready for the double bounce. Still 1/2 of 60. And then times 36. And then over here, all of the energies bounced into just the one kid. So I'm going to put in his mass of 60 times 9.8 rounded up to 10 for gravity, and it looks like we're going to be solving for h. And a little while later, you could actually go in and get that value. Okay, that's pretty much how to solve this. I think he ends up going like a good 10 meters. Basically, when we were doing this, it was at night. All we heard was a tree nearby rattling and then a big thump. And yeah, it was pretty good, except for his wrist. That's bad. Okay. Hey, here's one more thing for the rest of the PowerPoint. I have some solutions up here real quick for slides 17 through 23. So for example, for the roller coaster, you're going to calculate potential energy, and the unit label needs to be joules. For Wile E. Coyote, you're going to set up a conservation problem where the potential energy that he starts with becomes kinetic energy that he ends with. Same thing with jackasses in a shopping cart. They start with potential energy, they end with kinetic energy. Both of these problems are mass independent, meaning that since it's the same object the whole time, it's always the same mass, which means it divides out of all the different parts of the equation. Hydroelectric dam, you kind of calculate work done. For the coasting bicycle, it's a trick question. For the light bulb and the motorboat, you're going to use the power equation. So here's the answer key up for that. Hopefully that's helpful. And you guys, I think, are good to go for the handout now, if this all makes sense and you go through, take your time, etc. And again, I'll try to be back as soon as I can to help out.